Good afternoon. My name is Josep Medina. I'm a professor at the Universitat Politécnica de Valencia in Spain. Today, I'm here to present an ongoing collaboration between the Universidad Nacional Autónoma de México and my university. The purpose of this presentation is to describe the homogeneous low-crested structures for beach protection and to regenerate coral reefs. The presentation is divided in 5 sections. First, my colleague Edgar Mendoza will give a brief introduction to the retreat of the coral reefs and the problems associated with. Then, I will describe the homogeneous low-crested structure made of large rocks or concrete units. After that, we will introduce the placement grids, the importance of the placement grids, which affects the elevation of the structure on the crest freeboard. Later, Dr. Mendoza will describe the 2D physical tests made in the Universidad Nacional Autónoma de México. Finally, we will draw some conclusions.
For the last 40 years, coral reefs around the world have been reported to retreat at a rate of 1 to 2% per year. The causes may be largely discussed, but the consequences are that these important ecosystems are rapidly being degraded, and also that the ecosystem services they provide are being lost. One of these services is coastal protection. If coastal protection is lost, then the beaches that support industries such as tourism would also be degraded. And this means that a lot of social problems could arise in countries that depend on tourism. One alternative to solve this problem is the use of homogeneous low-crested structures made of big elements of rock or concrete. These structures could be considered as green infrastructure in the sense that they can mimic some of the functions of natural reefs, such as habitat providing and coastal protection. And they can also release the pressure induced to natural reefs and let them recover and reproduce. An example of this is Puerto Morelos in Mexico, where the coral reef has suffered from bleaching and other diseases. This, in combination with infrastructure constructed on the beach and the waves and currents produced by hurricanes, have resulted in severe erosion in the beach. To contain the beach, an artificial reef was constructed in 2010, and after that, monitoring has shown that the beach has recovered a state of resilience and a lot of integrity. But most importantly, we have seen that coral species have colonized the artificial reef, and also that seagrasses have recovered and the ecosystem connectivity has come back in a very good way.
Conventional low-crested structures are usually good solutions to protect eroding beaches. But large rocks are not always available near the construction site, and the permeability in the core is low. For that reason, it seems that homogeneous low-crested structures made of large rocks or concrete units can solve these 2 limitations and be useful to protect beaches in the short term and to regenerate coral reefs in the long term. The homogeneous low-crested structures have some advantages on the conventional low-crested structures, such as versatility. They can be built with or without large rocks around the construction site. Easy dismantling, reusable units. They have high porosity. They can attract fish and make easy the coralline colonization because of different exposures to light inside the structure. The functionality is similar but with the additional advantage of the coralline colonization and the regeneration of coral reefs. One special characteristic of these structures are the importance of the placement grid. The placement grid affects the layer of thickness and the elevation of the structure, and so affects the crest freeboard, which controls the wave transmission. For that reason, it's very important to relate the placement grid with the layer thickness. This is a picture of a physical experiment carried out in the laboratory, in our laboratory in Valencia, to estimate the layer thickness corresponding to different placement grids. In the master thesis of de Keysler and Jacobs, the methodology and the results for different placement grids were presented. On a flat horizontal bottom, different layers of Cubipods were placed with different grids, and with a laser, we calculated the thickness of each layer. A different problem is the placement on an irregular bottom. To design these placement grids and to face that problem, we use the Blender open source software. This is a physical game engine with a rigid body performance and collision detection. In the master thesis of Ricardo Centi, the methodology and the result can be found. In this master thesis, the frictions, the restitution and damping and rotation coefficient were calibrated with a few experiments, and later other placement grids and other experiments were made numerically. We found that the numerical method found similar results than the physical experiment on an horizontal bottom. We expect that this software can be used also for irregular bottoms. This is a picture of the behavior. They reproduce approximately what was found in the physical test. We put plates on top and calculate with a laser the thickness of each layer.
The experiments were performed at the National University of Mexico. There, several cross-sections of Cubipod homogeneous low-crested structures were tested. We used two different sizes of Cubipods to have two different geometric scales and account for scale effects. Cross-sections with 1, 3, and 5 layers of Cubipods were tested, and all the structures were placed over a gravel bed in order to reproduce bottom friction. These are the dimensions of the wave flume at UNAM. There, we have a piston-type wave maker equipped with an active absorption system. In the table, you can see the prototype values of the wave conditions we used in the experiments. As you can see, we tested different wave stiffnesses, mean regime waves, and storm conditions. All the waves were generated on the Jones-Swap spectrum. The waves were measured by gauges, separated according to the rules by Mansard and Funke to separate incident and reflected waves. I will show you some of the results of the stability during the experiments. For the one-layer structure, which is thought only for being used in very shallow waters, we found good stability, and during the storms, a slight displacement of some of the Cubipods. For the three-layer structure, we found visually that the number of Cubipods at the crest is very important to control wave transmission. And we found during the storms, some deformation or cubipod movement in the middle layer. For the 5-layer structure, we also found good stability for mean regime, but for storm conditions, we found deformation close to the area where the waves break, which corresponds to the 2nd and 3rd layers. And some of the cubipods placed at the crest were pushed towards the leeward side of the structure. Next, some implications of hydrodynamics will be explained.
After the 2D test, we analyzed the incident and reflected waves of all the experiments, and we estimated formulas to calculate the reflected, transmitted, and dissipated energy. With that, we can design 1-layer, 3-layer, and 5-layer cubipod homogeneous low-crested structure with a given placement grid, and we know what are the wave transmission for that, and also the stability. At this time, to draw some conclusions for this short presentation. First, we have to remember that coral reefs are retreating about more than 1% a year worldwide. And homogeneous low-crested structures, it's a new tool to protect beaches and also to regenerate coral reefs. The final goal is to have more resilient ecosystems. This new tool can be used to regenerate the coral reefs and protect the beaches, and also to create new structures to attract fishes and also tourists. So we need this multi-purpose green infrastructure that we can use to improve beaches and corals. Thank you very much for your attention.